Hey, Physics 30s, how's it going? So we're going to go over this 2009 diploma released items. Hopefully this goes well. Okay. So let's see if I'm using a different program here to write right on top of the PDF. So here's the answer key. Not concerned about that. We'll figure out the answers. Maybe we can review back there and see, did I do these correct? I don't know. Okay. So let's try out this first question here. So we have a child catches the ball, exerts a force F on a moving ball over a certain time period. Okay. The mass of the ball is 250 grams. The velocity changes from 5 to 1, so it slows down as a result of the force. What is the magnitude of the impulse? Yeah, this seems like a pretty simple little question. So remember, impulse can be calculated two different ways. So impulse is being the change in momentum, can either be force times time, if they gave you those two things to you, or it could be change, mass times change in velocity, right? So since we have the mass, which I'm going to change to kilograms, and we have the velocities, final minus initial, both are positive answers, so that's good. I can just quickly punch these into my calculator here. All right. So they always start this off kind of nice and easy most of the time. So we get 1. I don't know why I typed that in my calculator. It's just negative 4 times 0.2. So technically we get negative 1.00 Newton seconds, right? But they just want the magnitude, so it's going to be 1. Not too bad so far. If you catch the ball, and the ball has a applied force triple, and the length of time, what would happen to the length of time? Okay, so the impulse is going to stay the same, right? So if this impulse stays the same, then I can just look at that first formula there and say, okay, what would happen if I change something else to the time? What would happen to the time? So if I rearrange this for time, I can get impulse divided by force, right? So my time, well, if I get my new time here, so remember that little prime doesn't mean it's a derivative or anything. It's my new time, this little prime. If I triple this, that becomes 1/3 of these older numbers, right? So that's what I'm looking for here. It's 1/3 of my older numbers. The older numbers was time, so it's 1/3 of my time. What does the work represent? Or so no, what is the area under this curve? So it's the force time. Remember, force times time is impulse. So it's got to be my impulse. My force, length times width, area, length times width. This is like, I'll just put it here, length times width. That's the area there. Yeah. It's equal to my impulse. Okay, so we got two laboratory carts here on a frictionless surface. The spring attached to both is compressed, it holds them together, and then it cuts it. The string is cut, one cart moves 0.8. They're probably going to ask us what happens to the other cart. Just one question? Yeah, just one question. What's the speed of the other cart? So cart 1, I'm just going to write the speed beside it. Afterwards is that, to start off with, they're both 0, right? And since they're both 0, their momentums, which is mass times velocity, is 0 for both of these, right? So the sum of the momentums is going to add up to 0. So that's going to be very useful. So the sum of all my momentums before is 0. So that means the sum of all the momentum afterwards has to add up to 0 for an isolated system. You got a frictionless surface, all that stuff here. So the momentum afterwards, oh, I don't know what that symbol there is, after, okay, it's got to be 0. So when I add these two momentums together, I'll just put a sign convention here first. I was just going to say it that way, it's positive. So cart 2 will have the positive velocity. So if I take my momentum on my cart 2 and I add it to the momentum of cart 1, it should add to 0. So momentum of cart 2 is going to be its mass, which is 2.5 m times whatever velocity it happens to be. I just don't know what velocity is right now. Yeah, that should say 2 there. I wonder if we can fix that next there. Okay, let's fix that. Okay, it's velocity of cart 2 minus or plus a negative number. So I'm just going to plus here. Its mass, just m, times its velocity, 0.8 meters per second. So this m is not meters, it's mass, right? So the goal is to get the mass by itself. So I can see that the mass is common between these two terms here. So I'm going to minus that out. So m bracket. Actually, do we know the mass? Oh, yeah, okay. Never mind. The goal is to get the velocity by itself. I'm going to factor out the m, but then I'm just going to divide it out anyway. But yeah, let's do that. Let's do that instead. Seems like we could just bypass that first step here. So I'm going to take this mass here. Because it's equal to 0, this is allowed. Divide by m, divide by m, divide by m. No more masses. Okay, so all the masses are gone. Because 0 divided by mass is 0. Here we just have 2.5 v2s minus 0.8 meters per second. And my goal is just to find what v2 is. So let's just do that. So I'm going to add over the 0.8 to this side. Divide by the 2.5. I'm not going to show that step. 0.32. There you go. Cool. So here we got two cars. Or not a car. I got a train and a car. They're going to come and they're going to collide into each other. Can I get this so my face disappears? Okay. And when they collide with each other, I just want to know what the total momentum of the system is afterwards or before. Doesn't really matter. Immediately before, immediately after. So the total momentum. So I'm going to add these two momentums together. So the first thing I want to do is I want to find these momentums. It's going to be mass times velocity. So here I got 50,000 times 10, so that's 500,000. Kilogram meters per second. I'm just going to say east and north are positive here. And then down here, I'm going to do the same thing. Momentum mass times velocity, 1,200 times 25, 30,000. Kilogram meters per second. Kind of missed the G on my kilograms, didn't I? Okay, so I'm not going to be able to just add them together. So cross those ones off, right? Because they just literally added the two numbers together, but they're not collinear. When you're adding vectors, because they are vectors, if they're not at the collinear to each other, we have to add their x's and y's. So the x and y of this top one, if I were to, I'll just write down this side. Its x value is 500,000, and its y value is 0. Right? And this one, if I do the same thing, it's x and y values. This x is 0, and this is going to be 30,000. Right? So what I'm going to do is I'm going to add all my x's and y's together, which is pretty simple. So I got 50,000. These are momentums. 30,000. If we want to put some units in there, we can. And then I'm going to put these together. So how I'm going to do that is I'm going to draw a vector diagram here. Let's pick a different color. Let's go green here. So I'm going to go a little bit or a lot in the x direction, and then a little bit in this direction. So I've got 30,000 going up. I got 50,000 or 500,000, sorry, going that direction. My goal is to find that hypotenuse, which I think is going to be 501. based on the answers. But my real goal is to actually find out what this angle is. So I'm looking at that right now. That's definitely going to have to be B because the angle's small. Got a small y value, got a huge x value. It's going to have a small angle. But let's just double check that. So to find the angle, I'm going to go tan inverse my opposite, 30,000 divided by 500,000. So that's just really 3 divided by 50. 3.43 degrees. Cool. Pythagorean theorem, x squared plus y squared is equal to that p that we're trying to find squared. So 500,000 squared plus 30,000 squared to the square root. So this ends up being 508.99 kilogram meters per second. There you go. So that answers out to B there. Okay, so a positive charge is brought near to but does not touch, right? Does not touch one end of a neutral rod on an insulated stand. The opposite end of the metal rod is grounded. The ground is removed, then the positive charge is removed. So, okay, so let's go through the steps. What I know is what's going to happen is going to have a negative net charge. I always do the opposite. But why? So my first step here, here's my rod on my insulating stand, all right? That's the neutral one. A positive charge is brought next to it. So this is a nice positive rod. So what's going to happen is that's going to pull all of the electrons in the rod, all my electrons, are going to move over here. They're all going to move to the front. All right, so they're all going to move as close as they can to this here. All right, so what's going to look like afterwards is this is still here. There's my metal rod. All right, and all of the electrons are going to be sitting on the rod near this piece here. So if I ground this thing, so if I put a ground to it, here's my ground symbol. So what's going to happen is that more, because this end's going to be exposed, it's going to be a kind of positive. So what's going to happen is electrons are going to come up from the ground to kind of fill in that void. And then if I remove it, so my last step here, those electrons are trapped in there. So now I just have a lot more electrons than I had before. So this thing's now going to be just a big electron mess. Way more negative electrons than there were before. They're all going to distribute themselves out nicely as much as they can, but there's going to be a lot more than there used to be. Right? Because we didn't touch it. If we touched it, it would turn positive. Okay, so we got these two charges here, 1, 2, 3. What's the electrostatic force on 3 caused by 1 and 2? So 3 is way over here. Electrostatic force can go through other objects, like if you ever, I don't know if you ever tried it, but a magnet on top and bottom of your hand, it would just stick there. So those fields can go through each other, and they do add on. So first thing I want to do is I want to determine what direction the forces are going to be. So when I add them, I know what direction they're going to be. So I got a positive, negative here. So 1 and 3. So I'm just looking at 1 and 3. Positive, negative. There's going to be an attraction force here caused by 1. All right. And then these two are both positive. So there's going to be a repulsive force between these two caused by 2. So they're going to be going opposite directions. So let's do the two calculations here. So FE, I'm going to do 2 first, is going to be KQQ over R squared. Distance in centimeters, so I want to change that. I got these micros here. So remember, micro stands for times 10 to the negative 6. So when I put these numbers in, I have to be very careful about those units. And my distance is going to be 0.1 meters squared. Okay, so this one, 8.99 times 10 to the 9, that's the K value. Times the 3.5 times the 2.8 divided by the 0.1 squared. So this force is going to be 8.8122 newtons. And that's going in this direction. So I haven't created a sign convention yet, but that's probably going to be positive for me. And the other one, this is for number 1. So when I do KQQ over R squared, remember R stands for the distance between the objects. Again, I'm going to change these units. I'm not going to put the negative in, right? Because I know which way it's going already, so I don't have to worry about, oh, I got a negative. That means there's an attraction force or something like that. Draw the picture ahead of time. Draw the forces out. So you know which way they're going. Don't put anything in there. You know, so even in the formula there, it doesn't even have, it has absolute values on it, so it just gets rid of those anyway. Now this is going to be my total distance, so the whole 30 centimeters. So 0.3 meters squared, so that's going to be very important there. So 8.99 times 10 to the 9 times 6.5 e to the negative 6 times 2.8 times e to the negative 6 divided by 0.3 squared. So make sure you square that. And this one is not going to be as big, 1.8179. Bunch of decimals there, newtons, but that's going the other direction. So let's just say that this one's negative and that one's positive. So when I do my F net, let's just make my F net black again here. When I add these together, I'm going to be adding the 8.8102 with a negative other number. So technically I'm minusing it. So I get 6.99 newtons. Ended up being positive. So I don't have a sign. Maybe I'll just put it right up here. That way is positive. So that means this ended up being right. Didn't have any other option. They're all right anyway, but that's fine. There you go. If you forgot to change it from centimeters to meters, you probably would have got like A or something. If you just added them, you probably would have got D. You got to watch out for those directions. All right. This one here, I want to know the direction of the net electric force on L due to K and M. And which way is the field going at point P? So what's the direction? They're approximately the same part. Equally spaced. Okay, that's good. So the equally spaced K is a little bit larger for the charge-wise than this one. They're both positive, so that's a positive number. That's a positive number. L is a negative. I'm just going to put that down here. I'm not too concerned about that. Well, actually, I kind of am, because that means the forces are attractive forces here. So if I color code this again, so this green one here is going to cause an attraction force on this one, that way. And this one here is going to cause an attraction force, positive, negative, not as large as the other one, right? Because this is 3 and that's 2, the F on the L is going to be pushing it a little bit more to the left here, to the left of the page. Makes more sense. At point P, now on point P, if I look at this, and I'm going to draw my picture, it's going to be mostly towards the bottom of the page, right? Now the reason behind that is Q is going to have an electric field. If we draw my color codes here again, okay, it's going to have an electric field kind of out at this angle. Pause. All right, so that one's got an electric field going that direction. And then This one here is an electric field going this direction. The electric field, the green one there, caused by K, is going to be a little bit more than the one caused by M. But this one that's going straight down, I'm going to make that one orange there. Remember, electric field, like if it's positive, it's going out. If it's negative, it's going in. Okay? I'm going to maybe put that down in question 9 there. But L it's way closer, it's way larger. It's got this huge electric field going straight down caused by L. So if I kind of add those together, K and M, we're gonna have a little bit more to the right, but it's gonna be huge downwards, mostly downwards. All right? So just kind of remember, positive, the electric field is out. And negative, electric field is in. Okay, good. All right, so now, we're going to take these charges here, the 3, the -5, and the 2, and they're going to start touching each other. So I'm going to just put down, what's the order? KLM, KLM. So what have we got? 3, -5, and 2. 3, -5, and 2. They all have an X, but I'm not too concerned about that. Okay, after the first step. So after the first step, K and L are going to add. So if they're the same size, and they're made of the same material, both same conductive activity of both of them, when you touch them, the electrons are just going to distribute evenly. They're going to keep the charge. So I look at the overall charge. So I'm going to add them together. So if I add these together, I get -2, and then I split it up. I'm going to get -1 each. Okay. So we're going to add them together, and then we just divide by 2. Okay. And then we do the same thing as step 2. In this case, I'm going to take K and M and add them together. So that gives me 1, and that's going to give me a half each for those. And this one I didn't do anything with. And then my last one here, I'm going to take L and M, add them together. So -1 plus a half divided by 2. So we get a quarter each. -1/4. So we got a -1/4, -1/4, and a half. So which one matches? D. Now, if you wanted to go through it, like, I was trying to figure out, they all add up to 0, because technically the charges all add up to 0. So if I add to 0, they would all be 0. Like if I touched them all together and then separate them all, A would be the answer. But because I'm doing the step by step, I'm just kind of moving the charges between the two. Okay. The electric field at a distance of this is a simple question. This is kind of a weird numerical response question. Okay. So to find that electric field, I'm just going to be using this formula. Remember, electric field is the E with a line on it. This is electric field. All right. Very key. I'm looking for the field. So it's KQ over R squared. Just making sure all my units are in the proper thing. So these are already in coulombs, so I don't have to change it from like microcoulombs or anything. And then the distance here, I'm going to want to make sure that is in meters. Let's square that. Okay. So 8.99 times 10 to the 9 times 10 to the -5 divided by 0.04 squared. Just making sure to square that number. Okay, so I get this really big number. Yeah. I think so. So I get 6.7425 times 10 to the 7 newtons per coulomb. All right. Now in my boxes here, if I were to fill out the boxes, I'd have 4 boxes, and then I got to go A, B, C, D. So I got to go 6, 7, 4, and make sure to round properly here. I don't have to worry about rounding too much. And I get 6, 7, 4, 7. I just want to go up here and double check. Did I do that correctly? Yeah, look at that, 6, 7, 4, 7. All right, next one. Two parallel plates, 3 centimeters apart. There is 44 volts between them. The electric field that is 1 centimeter away from the positive plate is what? Now, we did this one in class, or depends on who's reading this thing. This is kind of just a red herring. Like, remember that the electric field between two plates, doesn't matter where you are, the electric field is constant. Right, going from the positive plate to the negative plate. Right, so from my positive plate here to my negative plate, that electric field is constant. Doesn't matter where you are. Right, if you're 1 centimeter away from the positive plate, if you're 1 centimeter away from the negative plate, if you're right dead center in the middle, if you're right against one of the plates, that electric field is going to be a constant number, so it doesn't really matter. You just said when we do this calculation, let me just write out the formula that we're going to use. When I do this calculation, which is delta V divided by D, those two numbers correspond with each other. Since the 44 volts is between the two plates, I need to know the distance between the two plates. So I have to use the numbers that go with each other. So I'm going to use the 44 and the 3 centimeters. And we get 1,467. Actually, a bunch of volts per meter or newtons per coulomb, whatever you want to write there for units. Those both are acceptable for this one. Again, I just want A, B, C, D. So my boxes here. One, 4, 7, 3. 1, 4, 7, 3. Cool. So we got an oil droplet that is suspended. Key again. So we got a suspended oil droplet. Has a pretty significant mass, so that means that gravity has got to be balanced out with something. So here's my oil droplet. We got gravity pulling me down. So what's pulling me up? Well, most likely going to be my electric field, right? Electric force, sorry. So those two forces are going to balance each other out. How do I calculate them? Well, one's mass times gravity, and I got the mass and the gravity. That's good. And then how do you calculate Fe? Because we're talking about parallel plates, right? There's so many charges in parallel plates. My Fe cannot be the KQQ one. It's got to be the, I don't know if you can see it here, the E times Q formula. Oh, it's right there at my corner of my head. Oh, that side. Right there. All right? So we got to use that one. We can't use the one up there because that requires just like 2 charges. But there's so many charges in here. So I can't use the other one. So I got to use E times Q. So I just want to find out what Q is. So I'm going to take this, divide by E. I don't think I have to do anything else, do I? You got electric field. They got distance between the plates. But why do I add the distance between the plates? I don't necessarily need that information. That's just there to throw us off again. Sometimes sometimes I write my numbers in, sometimes I don't. So here I get 3.2373 times 10 to the negative 19 coulombs. Now remember, an electron, one electron is 1.6 times 10 to the negative 19. How many of these fit in there? Well, it's obviously 2 of them. All right. Let's just divide there. Okay, got 2. The magnetic field created inside the solid. So remember that when we create magnetic fields, they produce loops. So here, I got electrons coming out the shorter side. So even if they didn't put the negative in there, remember that the electrons come out of that shorter side. It's going to come up over the front and then down the back. Right? Over the front, down the back. Over the front, down the back. So there's my electrons. So what I'm going to do is use my hand rule. So just 1 second. I'm just going to change this so I can actually do this. Okay. So I'm going to use my hand rule. So I'm going to make sure my fingers curl in the way that, let's just kind of make sure how this is going to look on my screen here. Yeah, so it's going to be that way. So my fingers are going to curl in the way that the electrons are going, and then my thumb, and I'm going to be using my left hand, my thumb is going to be pointing towards where the north is. So I just got to look at my screen here. So my fingers are going to curl around the front and then down the back. My thumb points towards one side, and then based on my hand, yep. So my thumb is pointing this direction, so that's where the north is. Okay, use my left hand because we're talking about electrons. Curls around, thumb points that direction. Now we just have to figure out which way the magnetic fields are going. So the magnetic fields are going to come out of the north. Okay, they're going to loop around, come into the south, right? But continue through. They make loops. So while they're inside and worry about what's inside the solenoid, they're going from left to right here, towards the right of the page. You got to remember your left and rights. Sorry if you can't. So I'm going to draw a little picture here. I don't know if I can do this very accurately. Sometimes I can draw a good hand. Sometimes I can't. Okay, so I got a hand. This is my thumb, and these are my fingers here. There you go. So I draw my picture here. So this here is the direction of my electrons. I'm using my left hand, right? Left hand, and my thumb points towards the north. There you go. That's best my ability of drawing a 3D hand. I'm sure if I took more time I could do it. There's a bunch of space down here. What a waste. Okay, so we got a negative charge particle traveling into this magnetic field here. So now the magnetic field, if I were to draw that in there, it's going from north to south, just kind of describe like what we did up there. So we want to determine the direction of the force acting on it, so Fm. Okay, so again, we're going to use a left-hand rule. So I'm going to draw a left hand here. So how this is going to work is that straight hand rule, right? This is the... Okay, so there's my left hand, all right? So my left hand is in a kind of an orientation where it's kind of pointed down, right? It's kind of hard to do, so it's pointed down like that. So my fingers are pointing down. Now, why I'm doing that is that, remember that the magnetic field goes in the direction of your fingers. Your thumb is the direction of the charge. And again, this is my left. Left is negative. The thumb is the direction of the particle, and your palm is the direction of the force. So I don't know what color I can put that here. Orange? No. Let's go with that color. So right there, that's my FM right there. So my FM is out of the page here. Right there, out of the page. Cool. What's a good approximation of the units of the magnetic field strength? So that's B. So what are the units of B? Or like a Tesla, right? A Tesla. What is a Tesla? So if I use my formula, FM is equal to Q. They use amps in some of these, but they also use coulombs and meters per second. So I don't know which one going to be the best situation here. So let's start off with the amp one. So ILB. I'm going to rearrange that for B. Yeah, let's just rearrange for B first. FM divided by I and L. So FM is in Newton. Sorry. I is like a current, so that'll be an amperage, and L is in distance, like in meters in length. So, nope, these ones don't look like they could work out. So it's going to be one of these other two. So another way to represent an amp is that an amp is the same thing as a coulomb per second. So I can do it that way too. Remember, that's just I is equal to Q over T, right? Oh, my head's getting in the way of this picture here. Q over T. So I could put that into this formula here. So that means a Tesla is going to be a Newton over a Coulomb per second meter. And then remember, a denominator to denominator, or you could just do the keep flip change. You got to flip that piece over and you get this. So that part flips over. It's going to be D. Right. Got to have the seconds on the top and meters on the bottom. Cool. You could have done with the other formula too. Without QVB. Okay, so we got a current carrying wire here. The magnetic field strength is this. The current is that. The wire perpendicular. The length of the wire. Okay, so this is weird. This seems pretty easy. FM is equal to ILB. Okay, I didn't say that in that order, but that's fine. We're looking for length, L. So we take our FM divided by I and B. And we got everything. This is, maybe they're just figuring out, can you divide by two things? I don't know. It seems like a weird number, or pretty simple question, sorry. All the units are this good. So we got newtons, we got amperage, we got our field strength in Teslas. Now, what they're doing here with the units is that they put this little negative W here saying that they don't care what the W is, right? What they care about is the numbers of the scientific part in front, like the sig digs. Knowing that this is -2 doesn't really matter. But they are giving a hint that it's supposed to be a negative number. So that's good. They don't know how many digits it is, but that's okay. So we want 3 decimal places here. So in my boxes, what I would fill out here, not 3, I want 3 sig digs. So I'm going to go 6.24, which is proper scientific notation, right? So making sure that decimal is right after that first sig dig. Let's just double check. Oh, yeah, 6.24. Cruising along here. It's this big long question. Where are we right now? Oh, 30 minutes. Okay, that's too bad. Okay, so we got this huge question here. I'm just going to read through the questions first. What's the magnetic field? The magnitude magnetic field in the lens? What's the instantaneous radius? So I'm just going to kind of write some things down here as I go. So here we're looking for B. What is B? Here we're looking for R. Knowing that, we're probably going to start off by saying, let's say FM is equal to FC, because we talk about circular motion, MAC, QVB probably, QVB. It's probably not talking about a wire. And we're just going to rearrange for R, but the R is going to be inside that part there, the V squared over R. So remember, you have 2 choices for AC. Most of physics time, for physics 30, we use the V squared over R, not the 4 pi squared one. And then we just rearrange this a little bit, and then we'll deal with finding the numbers later. This is me just kind of thinking about how I would solve this question. So times about divided down. I haven't crossed off those V's yet, but that's okay, because I'll do it right now. Gone. So it's just MV over QV is equal to R. Okay, so I'll find some of those numbers later. The collision that produces backscattering electrons is classified as elastic. So when we talk about subatomic particles, there's no other place for the energy to go. Right? We're not producing new bonds. They're just bouncing off each other. If there's no way for the other particles, because it's mostly empty space, there's no other particles that take the energy away. So I'm going to assume it's classified as elastic at this point. and because the kinetic energy has no change. If it's elastic and there's a decrease, that makes absolutely no sense. Inelastic and no change make no sense. It's got to be either B or C. My guess for a good answer would be B on this one. All right? Oh yeah, there's no. Yeah. Okay. When we talk about subatomic particles, elastic collisions. In the bigger world, where there's lots of particles and air molecules and stuff that can take energy away from the system, it's most likely not going to be elastic. 99% of the time for those bigger ones, that's true. Okay, so keep on going. All right, the wavelength can be hypothesized by this h over p, momentum. A microscope, whether it uses light or beam, has a resolution that's approximately 2 times the wavelength of the wave used. Okay, the reason that electrons have a higher because of shorter wavelengths. Yeah, that makes sense. Shorter wavelengths. Oh, not longer wavelengths. What am I thinking? Let's go back up here. Where's my undo button? I'll just erase it. Meh. Shorter wavelengths, because it's very key in this one here. They talk about the key here. The resolution is approximately 2 times the wavelength of the wave, right? So the smaller the wave, the smaller the resolution, the more I can see. So I'm assuming shorter wavelengths here. Okay. In order to achieve this resolution, what must the speed of the electron be? So I want to achieve this resolution of 1 nanosecond, which is, the resolution is approximately 2 times the wavelength of the wave you lose. So this is the resolution of that. That's twice the wavelength. So that means the wavelength is half of that number. Okay, so my wavelength is 1/2 of this resolution, according to that underlined part up there. So the wavelength is half of this number. Let's just write out some numbers here. And what are we trying to find? The speed of an electron. So we can use this formula here that they spit up on us. Remember that P is equal to mass times velocity. That's what we're trying to solve for here. So if I rearrange this for speed, times it up, divide down the wavelength, I can put all the numbers in here. You know, I kind of skipped past a bunch of those questions. I'm going to go back to them. Don't worry about that. Now remember, for this formula, the h I'm going to have to use 6.63 times 10 to the negative 34. So I have to use that one, just because that's the one you have to use for that formula. Mass of an electron, 9.11 times 10 to the negative 31 kilograms. And my wavelength, I've got to change it into regular meters, dude. Okay, so let's see what this ends up being. Pretty fast. 1.4, what do we want? Okay, 1.4, I'm going to put a bunch of decimals here. Times 10 to the 6 meters per second. It's 1 million, yep, that makes sense. So in my boxes here, so we didn't need the other information to do this question. Oh, I want A, B, C, D. So I want 4 here, and you have 6 here, and then a 6 here. So 1466. Cool. Again, they give us hints so that it's a positive exponent, so it's going pretty fast. And they want the A, B, C, D. No decimals here. Okay. So let's go back. Let's solve the rest of these questions. I don't think oh, this is a different thing altogether. Oh, is this still in the SEM? Well, let's go back and finish those other ones before I go too far ahead. All right, so we got this electron here. Comes in at a speeds of 27-ish or 26.5 million meters per second. Has a magnetic force acting on it. That's all we have here. We know it's an electron. Okay, so this first one, because we're dealing with Fm, they give us a magnetic force, QVB. They give us the speed, and we know it's an electron, so we know all this stuff. So if I want to solve for B, I'm going to take my Fm and divide it by Q and V, and I know all those things. So the Fm up here, so here's my Fm. I'm just going to label it right on the picture. Oop, right on the picture. This here is my speed. Right. And we're talking about electrons. I think somewhere in here is about electrons. Here's electrons. So we know the charge of an electron. Okay. So I'll take my Fm. Divided by Q. And the V. Yep. Okay, so what I get here is 0.78066 Teslas, which if I were to put in scientific notation, with the 3 decimals and a negative 1 in that W spot there. But again, I don't care about that. We only care about this part, 7.81. That's all I care about. Okay, this one down here, so we know the speed, we know the mass, we know that, we know the B. Technically, we know the Fm too. I guess we didn't have to find this B value. I could just use the Fm that we had to solve for this as well, right? So if you wanted to avoid, if you didn't like your B value, like, oh, did I get the right B value? I don't know if I'm going to get the right answer. Maybe you could test it and see if you get something that's here. Or you could do this one, where you have Fm on this side of the equation. You're going to divide by, sorry, not divide by. We'll put a little or here. Or, okay. So looking for R, times the R up, divide that down. So it's going to be mv squared over Fm. So we could do it that way too, right? So both of these should give me the same answer because QVB, you notice that on the bottom there, QVB is just Fm. I'm going to use my B value with all the decimals, right? These numbers are pretty far off from each other, so even if you use the rounded number, it probably would work just fine. And I'm just going to put it in there. So 9.11 times 10 to the negative 31 times the speed. Go back to the speed here. Okay, divided by the Q, the electron, so 1.6 times 10 to the negative 19, times the B, which I have in my calculator. So I get C here. 1.9327 times 10 to the negative 4. Okay, just to double check, if I just use the numbers given to me in the question, what's the Fm? Fm is the 3.31 to the negative 12. Do I get the same answer? Yeah, I get the same answer. So if I just use the numbers given to me in the question, or this one I'm trusting in my B value, I get the same answer. Plus also I used the B value I got, and I got an answer here, so probably did the previous question correctly, unless they planned for some weird distractor. Okay, and again, question 16, if we're in the subatomic world and there's no air per se, other molecules that take energy away from the system, then the system's going to be elastic. Right? Energy is not going to be lost to surroundings because the surroundings really don't exist. They're mostly empty space. Okay, so last question. I think this is the last question. Oh, the last 2 questions. What do they say up here? It said to the next 10 questions. How many have we done so far? 1, 2, 3, 4, 5, 6, 7. Ooh, is there still more of it? Yeah, this is still more of the same question, but this is just like its own thing. Okay. Some of those electrons in the original beam. Oh, there you go. The original beam knock loose electrons from the lower energy. An electron from a higher energy will make a transition to fill that vacated spot, so they'll drop down. The following energy are two possible transitions. So we want to know what Ka is. So to find out what Ka is, we have to know what is the change of energy. Because remember, in these kind of things, if the electron loses energy as it drops down, it's got to release the same amount of energy. Because it's got to go somewhere. It can't go into the surrounding area to the air. So it's going to turn into a photon. So to find that, I'm going to go final minus initial. It's going to end up being negative. That's okay because it means it's losing the energy minus a negative number here. So final minus initial. I get negative 67.2 electron volts. Now, this is lost energy, so the photon energy that's going to be released here is equal to a positive this number. And then I can just use that to find the frequency. Remember, E is equal to HF. Let me arrange for F here. E, oops, my head's in the way here. E divided by H. Now, which H do I use? So remember, you want to pick the right H. And you want to use too many things, right? So there are some questions where like, oh, maybe I can use the Joule version, then I can convert it later or do all this other stuff. If you use too many numbers from the periodic table or from the formula sheet, then you're going to start getting rounding errors. You try to limit how many of those constants you use. So in this case, I'm just going to use the H value. So rather than changing it to joules and then using the other H value, which is using two constants, just use the one constant that corresponds to what we have. So this is going to be the 4.14 times 10 to the negative 15 one, I think it is. I hope it is. Is it negative 15? I don't have my, oh, I do have one right here. Cool. Yeah, negative 15. I'm using the electron volt version of this number, right? So I'm going to write that down. So 4.14 times 10 to the negative 15 electron volt seconds. So that crosses off. I'm left with per seconds, which is a hertz, which is good. So my answer is going to be, let me just write down whatever I have here. 16 hertz. It's pretty big. And put it in the boxes for this question. Again, I'm not too concerned about what the exponent is, but they're at least giving a hint that it's a positive exponent. I'm just worried about the 1.62 here. Okay. What's it most likely going to be? So what I want to do, because I don't remember frequencies, right? I remember wavelengths. So what I'm going to do, so I'm going to quickly change this to a wavelength. V is equal to F lambda, lambda, V F over F. V being the speed of light, all right? All photons must travel at the speed of light. I'm going to put this number in there. I'm going to just quickly change it to a wavelength so I can look at that number and say, oh, I know what that is now. Okay, I still don't know what it is right now, okay? Because it's in meters. So negative 8 meters. And I'm just going to quickly divide this by 10 to the negative 9. And I get 18 nanometers. Okay, so 18.48 nanometers. Okay, so looking at my options here. So remember, I should say, visible light. This is visible. Ranges from anywhere from what is it, 300 all the way up to 700 nanometers. So on this side, that's red. This side over here is violet. So I got infrared over here, that's longer. I got microwaves, that's even longer than that, right? Over here I have ultraviolet. Then we have X-rays. Then we have gamma, et cetera, right? Because this is shorter, we only have one option. It's got to be X-ray, because infrared and microwave has got to be more than 700, and this is less than 700 for sure. It's not within the visible range. These are too long, right? So it's got to be X-ray. Just because it has to be on the shorter side, and X-ray is the only one on the shorter side there. They try to make it as obvious as possible. It's either going to be visible or it's going to be very obvious which side it's on and which one it's going to be. Okay. The original electron beam can knock loose valence electrons from the specimen to detect a secondary electron. A scintillator or photomultiplier tubes are used. All right. For each secondary electron, man, some of the stuff these guys think of is crazy. So this a photomultiplier tube, a PMT. For each secondary electron hits a scintillator, the photon that has a wavelength of blah, blah, blah is produced. Okay. This photon hits the photocathode, which has a work function of 1.8 electron volts, and initiates a photocascade as illustrated below. All right, so it comes along, hits that, creates this photocascade. That's pretty cool. All right. Well, that's pretty cool. Inside a photomultiplier tube, there's several diodes and a final collector. Each diode is kept at a greater positive potential than one previous to it, and the electrical potential difference between the diodes and the next is 150 volts. All right, might be useful. Yeah, it's going to be more. The electron released from the photocathode is accelerated towards and collides with the first diode, releasing a number of tertiary electrons, which in turn accelerate to the next one. The process repeats as a million-fold increase in the number of electrons released by the time they reach the collector. This provides a strong electrical signal in response to the detection of a single photon. That is pretty cool. Yeah. The process by which an electron is ejected is called the photoelectric effect. Because we talk about the work function there, right? Right. So since I talk about the work function at that part, this is at the photocathode. They talk about that work function. So the work function is obviously the photoelectric effect, right? That's kind of a thing for that. The maximum kinetic energy of the speed electron ejected by that is this. Okay, so we're going to use that one of the formulas that's not used, remember? To find the energy of the electron that comes out, we have to know the energy of the photon that goes in, and then that's going to be used in two different spots, right? It's going to be used in the W and the EK. This is in the electron, and this over here is obviously the photon, right? So the energy is conserved. The energy of the photon goes in, disappears. It's be used for two different things, kind of dig its way out, and produce the kinetic energy. Okay, so the photon is this photon right here. So this photon is 4.00 times 10 to the negative 7. So to find out what that is, I'm going to go hc over lambda. Is that the formula for that? Yeah, hc over lambda. The work function, they give us the work function up here, if I read that correctly, 1.8 electron volts, and we're trying to solve for EK. So first of all, I want to find out what the energy of the photon is. And since I want this to be in electron volts, I'm just going to use the electron volt version of the number. Times it by the speed of light, divided by my wavelength. So I get a photon energy of. So that's got to go somewhere. it's obviously not going to be that or this one. Okay, those are too large. And it's going to be split between these two spots. It's going to have a little bit to dig out, and then what's left over goes into kinetic energy. So it's going to be 1. Actually, I probably should have just crossed off. A lot of these I didn't have to do any work for that. Could have just got A without a calculator. So I just minus this over, and I get my EK to be 1.305 electron volts. Okay, a particular electron leaves one diode, has a kinetic energy of this, the speed of this when it reaches the next diode. So that involves this 150 delta V here, the voltage. Okay, so we got an initial kinetic energy. So our goal is to find out what the final kinetic energy so I can find the final speed. Okay, so my EK final question mark. So to find the change of energy, I'm going to use the formula that is, oh, I can't see it. It's off my formula sheet. It's right up there somewhere. All right, it's going to be delta V is equal to delta E over Q. Remember, this energy change is either potential or kinetic, right? One goes up, the other goes down. So when I find the change of energy, I just have to think about what's happening in the question and say, oh, it's speeding up. So that must be a change of kinetic in the positive direction. So when I rearrange this, I'm going to get delta V times Q. It's a charge of electron. It's 150 times 1.6 times 10 to the negative 19. So I get a change of energy of 2.4 times 10 to the negative 17 joules. So that means, this is going to be equal to final minus initial. I'm going to add over my initial, my final energy, because this is a positive change, so I'm going to add them together. It's a very conveniently round number. So I don't know why I'm doing my calculator. 3.4 times 10 to the negative 17 joules. Now, it didn't ask for that. It asked for how fast it's going. So remember, this is going to be 1/2 mv squared. Why did I put the square there? What am I doing? Okay. V squared is equal to this number. Cool. Then rearranging that, times by 2. 2 times EK divided by mass. Take the square root. Finds my speed. So times the 2 up, divide the mass down, and then take the square root. The mass of electron, this is all about electrons. Take the square root. There you go. Okay. So my speed is 8.64 times 10 to the 6 meters per second. Sweet. There we go. Fun question. Which of the following sentences best describe the electric and magnetic field components of an electromagnetic wave? They are perpendicular to each other. They're definitely not parallel. The change in magnitudes are unrelated. Are they equal? Well, they're not equal, and they're kind of related. If one goes up, the other goes up as well. So they have the same frequencies and stuff, so... but they're definitely not equal, and they're definitely perpendicular. Yay, happy face. Okay. Okay. Michelson type experiment. Oh, this is fun. Another formula which we don't have on our formula sheet. Remember, to find the speed of light, we're going to take 2 times the distance it has to travel, times the number of mirrors there is, times its frequency. So it's 2 dNf. And we're just trying to find, in this case, frequency. This is per second, so this is going to be in hertz. So my frequency is going to be C divided by 2dN. Here, they only give us a one-way distance, so that 2 tells us that, remember, it reminds us that it has to go both ways. So if they already gave us the both way, then don't put the 2 in, right? The 2 is there to remind us that we have to go both ways. This has got to be in meters, because the speed of light's in meters, so this is 30,000 meters. Number of sides of the mirror, N is equal to 8. It's not bad. The speed of light. We're going to make the assumption the speed of light is, unless they give it to us in the question, is 3 times 10 to the 8. Cool. 2 times that 30,000 times the 8. So 625. Then they put in scientific notation for some reason. They did that because they wanted to make it match the other ones, right? It's just 3 sig digs, but the other ones would have been 3 or 4 sig digs. So or 4 or 5 sig digs, sorry. So they just did it so it all matches. Makes it all look nice when you draw that like that. Oh, this one. I like this one. Okay, in a laboratory experiment, we got... Oh, okay. In a laboratory experiment, sorry about that, I'm just going to check something. Make sure I'm not missing anything. Oh, I might be. Just 1 second. All right, so in a laboratory experiment, a microwave generator produced a beam of monochromatic microwaves. These waves are incident on a series of metal tubes. And they have a bunch of distances and a bunch of other things here. Oh, they got an angle, which is way larger than 1 degree. So we're definitely not going to use XD. And we don't use that formula, remember? We might use it to help us talk about how things could change, but never use that formula. But they give us an angle, so that's good. So we're going to use our formula here. Lambda is equal to d sine theta over n. So we got theta. Awesome, right there. Now, do we have d? The receiver is placed this many centimeters from the diffraction grating. The central maximum into position 1. Position 1 is the first order, right? Yep. This is the first order, so that means n is equal to 1. All right, and... oh, the tubes are this distance here, so that's my distance, and this is my L, all right? So, yeah, so what I want to do is I want to leave it in centimeters, so I'm going to leave this in centimeters, because everything else doesn't have units. So this is in centimeters, and I go sine 49.8. That has no units, because that's just a ratio between 2 sides or 2 somethings, and this 1 is just 1, so there's no units there. So it's just going to be a pretty simple calculation here. Man, this is a pretty nice test. 1.3748 centimeters. So if I'm going to put this in the box here, .37, right? Yeah, pretty good. Visible light has a wavelength of this, is directed onto fused quartz. Index refraction is in air. Okay, so the n values, a lot of these questions have n's, but they all mean different things. This is index of refraction, that's the number of the antinode that we're looking at, and this n up here is the number of mirrors. But that's okay. This n, so let's call that n1, let's call this one n2. It's 1.46. The wavelength that's inside here, so we're going to use Snell's law. So I pull out Snell's law, and we're going to deal with, what are we dealing with? The wavelength and index of refraction. So my index of refraction, n2 over n1, and then my wavelengths on the other side are going to be lambda 1 over lambda 2. So this is going to be lambda 1, because they're literally in the same sentence, so they would go together. And we're looking for the lambda that's inside the quartz, which is my 2. So we're looking for lambda 2. So if I put my numbers in, 1.46 over 1. On this side, I have 6 times 10 to the negative 7, because those go together. They look like they're across from each other. And then we're looking for lambda 2. So we do a little cross multiply and divide situation here. So cross multiply, divide. So I get 4.109 0.58 times 10 to the negative 7. Okay, I'm going to put this in a box. What do I need? So I don't care about the W. The W is just telling us that it's a negative exponent, which is good. That's what we got. And then it's going to go 4.11. Cool. All right. What distance from the page would a convex magnifying lens? This is an old question, so this is a diverging. The government has since changed the way I'm writing this thing, so this convex lens. No, this is a converging lens. That's why I always mess that up now too. So this is a converging lens. So that's what they would say now. All right, so they wouldn't say that. They would say converging. Okay. Focal length of this. So this is a converging lens. So the focal length is a positive 10 centimeters. Would be held to have the letters appear upright and 3 times as tall. So I want the magnification to be positive 3 because it's upright and 3 times. Okay. That's all we're given. I want up to 3 times as tall. So what I know, what are you trying? What distance from the page would a magnifying? So we're looking for like DO in this case. What is DO? We know that image is 3 times as tall. So if I use this information, M is equal to negative DI over DO, I can say that using like a system of kind of equations here, that I leave the 3 on this side. That through negative, so DI. Oh, we're solving for DO. Let's solve for DO. Oh, we're solving for DO, so that means I want to isolate for DI. Okay, that's the reason. Okay, so DI is equal to negative 3 DO. So that's what I know so far, right? So just putting the 3 in there, times the DO up, move the negative to the other side. So that's important. So why that's important is because then I can put this into this formula here. It's kind of like a little system of equations. So I know this is 1 over 10. I know DI is negative 3 DOs, and this is 1 over DO. And so now all I have is DO, right? Created like a system. So I took this. Yeah, I took this piece here, which is the same as that, and replaced it with this, right? Okay, so since now we have the same, we have one variable, we can solve for it. So I can times both sides by DO, get the DO up to this side. So we get negative 1/3 plus 1, and then I can just rearrange this after I 1 minus 1/3, and then times it by 10. So this is actually going to be 0.6666, and then times it by 10 to get rid of the 10 here. So DO is going to be 6.67 centimeters. There you go. It's a fun equation. I like that one. But you can always just guess check. Like you have lots of time during these tests to do that. Oh, this is bad. I don't like this one too much. A student uses a variable or various apparatus to investigate optical phenomena. During their investigations, they make the 8 of following observations, which could be produced using a triangular prism. Remember, a triangular prism is going to be like that one where you pass light in, the light is going to spread out and it's going to produce a rainbow, right? A rainbow. Oh, a rainbow. But it could do some other things too, but it's going to produce this kind of nice little rainbow. All right, so apparatus produces a continuous spectrum with white light. Yeah, you could definitely do that. All right, if you have white light coming in, cool. It could produce a bright line spectrum using white light. Maybe, because it depends on how the white light is made, right? So maybe if the white light is produced using like Like the white that's on the screen right now, that's right here. That's all that. That's just produced by 3 different colors. So I think what they mean by white light is the whole rainbow, right? Not a fake white. I'm going to put a little question mark beside that. So I have 4 spots, so let's figure that out. Produce an interference pattern with monochromatic light. No, that's a split. You can't do that one. So you can't do that. Okay, that's using like dual slits. Dual slit or diffraction grating. Okay, apparatus produces a single bright light with monochromatic light. Yeah, I guess so. One light goes in, it refracts, and it comes out as one light. It's not going to spread out because there's only one light. So that makes sense. Bends red light at a smaller angle than it bends blue light. That is true. So remember, blue light bends more. So shorter wavelengths, shorter lambdas, refract more. So they have a bigger bend to them. So that's true. Then obviously the next one's false, right? So we've done 3 so far. Apparatus produces a single spectrum when white light is incident, perpendicular to the apparatus. How do you come perpendicular? Because when it comes out the other side, it's going to have to spread out. Perpendicular to the apparatus. Produces multiple spectra. Oh, that would be like a diffraction grating. So this is like a diffraction grating. Remember, the diffraction grating, you get multiple spectrums. You get a bunch of spectrums on either side, right? So that's what they're talking about there. So they have light coming in, it diffracts, and you get these multiple rainbows. Here, there's only one rainbow, right? So you only get one rainbow. So the answer's got to be 1, 4, 5, and 7. Is that what they say? Yeah, it is what they say. 1, 4, 5, and 7. All right, so you produce a single spectrum, one rainbow. A single rainbow. Right? When you do that diffraction gradient, you got those rainbows on either side, and they just kept on getting bigger and bigger and bigger as it went out. But you have multiple rainbows. All right, so what do we have here? We've got a satellite is exposed to radiation. It causes it to be positively charged. So this is like the photoelectric effect. The radiation is going to bounce out electrons. So which of the wavelengths would cause the platinum coating to become positively charged? So we know the work function. So remember, this is the W, and these are all the energies up here. So we just have to make sure or not the energies, the wavelengths. If the energy of the photon is more than this number, then we're going to get ejections, right? So I'm going to write that down. If E photon is greater than W, then photo emissions are present. The photoelectric takes place. Okay, so we just have to find the energy of these photons. So remember, the shorter the wavelengths, the higher the energy. So I only have to do this calculation a couple of times because they're in order. They go to longer wavelengths. So once I figure out which ones work, so obviously one is probably going to work out of all these. All right, so I probably could cross off this one and this one because they're not talking about one. It's either 1 and 2. So I just want to make sure 2 works, right? So I'm going to use the joule version of the number 6.63. Oh, sorry, calculating the energy of a photon by going hc over lambda. I'm going to calculate these energies here. 7. So the first one is 8.84. Yep. So check mark. I didn't have any problems with that one. The next one, let's just double check that one. Delete. Okay. Oh, what am I doing here? This is all messed up. 3, 3, e to the negative 7. Okay. This one's going to be 5, 3. Just makes it just a little bit higher, right? Because the 3 is a little bit higher. And then if I double check the last with this next one, so I know it's not going to work, but I'll do it anyway. 3.24, 6. Not enough energy, right? So not enough. So it's got to be 1 and 2. Bam. Remember, this is that formula. This is the formula that we've been using for a couple of times. The formula which we you have to remember for like the last few questions here. This equation is derived from what? Well, it's all about energies here. So they tried to remove the energy part of this. W is the work function, which is energy. This is EK, right? This is the V stop part of this formula, right? That's how we determine those EKs. This is HF, that's the energy, right? So that's this HF part of this formula. So these are all energies, so this is conservation energy. Right? Remember, Compton also dealt with kind of the same idea. He used the same formula, or well, not really the same formula, the same idea, but with conservation momentum as well. That's Compton. Electromagnetic radiation produces wavelength incident on this. Which of the following graphs represent relationship between kinetic energy and the intensity of the light? So, remember, intensity just tells us how many electrons are coming out, not the energy of the electrons. Remember, it's a 1-to-1 ratio. So all the photons have the same energy. The electrons that come out will just have the same energy as well. So they're not going to change. I'm just going to have more of them, right? So like if I wanted to say like this, if I crossed this off and said this is current, amperage, that would be true, right? More intensity, more current, because I have more electrons, right? This doesn't make any sense at all, and this is just weird, okay? But if I want to make that graph true, this would be current. Okay. Which of the following conclusions most closely discovers the cathode ray? So who is the cathode ray? So we got Dalton was the first one with the billiard ball model. Then J.J. Thomson, then Rutherford, then Bohr. So J.J. Thomson was the cathode ray guy. Rutherford was the gold foil, right? So this guy here did the gold foil. Cathode ray was J.J. Thomson. Maxwell conclusion. So these guys were both the Bohr model, right? Bohr used Maxwell's conclusion. Yeah. Those are just observations, like what do you call it, like the emission spectrums. Observation. There was no experiment, just observations for that one. Right. Okay, let's go with that. One example of Compton scattering is below. The incident photon has this momentum. It collides with a free electron that is initially at rest. The scattered photon has a momentum of this, 85 degrees from the incident. What's the magnitude of the momentum of the free electron after it gets hit? Okay. So it's nice they gave us all these momentums, which makes our questions a little bit easier. So before the collision, so if I kind of put a little dotted line here, what kind of momentum do we have, right? So our momentum of our photon, this is before, is going to be 3 times 10 to the negative 23 Newton seconds. And if I break this up into its x and y's based on the picture, this looks like it's all x, but no y, right? The electron is at rest, so its momentum is 0. Its x and y's are both 0. Okay, so everything's got to add up to that x value that we have there. So afterwards, I can go through and just, so I have this momentum here, 1.73 times 10 to the negative 23 again, kilogram. Oh, they're going newtons per second here. This is Newton second, sorry. So we can use those same similar units. Okay. And then we can break this up into its x and y components. So we're talking about the photon. The photons is one that gets scattered upwards here. Yeah, let's use a darker color than that. Oop-a-doo. So I got to find this y, I got to find this x component. So using sine and cos. 1.73 times 10 to the negative 23 times sine 85 gets us our x, well, y value here, sorry. Sine gives us our y value because it's opposite that 85. I'm just going to write down a bunch of units here. More than enough for my sig digs here at the end. And then my cos, 85 gets me my x value, which is pretty small compared to the other numbers. Okay, then what's the electron? So the electron is no longer at rest. We're trying to find out what that momentum is. That's what we're trying to do here. What are its x and y? So that's what we're trying to find here. Now, all the x's and all the y's had to add up to what's on the previous side. So if all my y's, so if I just do this over here, the sum of my x's and the sum of my y's, everything's got to add up to these numbers. So everything's got to add up to y at 0. So that means this has to be negative. Nope. That's 23417 times 10 to the negative 23. Okay. It's got to be negative because it's got to add up to 0. And the x1 has to add up to this 1.83 number. And we have a little bit of x here already, but they got to add up. So I'm going to like minus it over to the other side to figure out what's left over. And I get 1 point negatives technically, because it's going down. Oh, is it negative? Oh, it's positive. This is x. It's positive. Negative because the y is negative. Okay, that makes sense. 679. So it's approximately, they say 45 here, but it's not actually 45 degrees if you actually go through the math of this. That's fine. I think we're just trying to get something approximate. So to find out what this momentum is, we use Pythagorean theorem, right? So what we just found out is our x and y pieces. We just found these x and y pieces here. And now I can put them together. So momentum squared is equal to x squared plus y squared. So I'm going to take this number, I'm going to square it. I'm going to add it on to the other number that I have there. 723,417 negative 23 squared. Take the square root. And I get 2.4. 2.41 technically. But I think maybe the closest value here that we have here, negative 23 Newton seconds. So I don't know why they switched their units all of a sudden. It's kind of strange. Who was writing this test? So, D. I don't like that because they gave us that 45, but it really wasn't 45 degrees. It was something else. It's like 40. Well, I just want to double check that angle actually. What would have been not 4.67, 1.67. Oh, I said 46 degrees would be better. Whatever. Get a close answer. If you used a 45, you probably would have got this answer too. Which of the following produces a continuous spectrum? Gas is not going. This is going to produce a emission spectrum, a bright line. Right, spectrum. Light emitted by a cool gas when passed, and then light emitted by a cool gas and then pass through a hot, dense solid. A hot, dense gas. This wouldn't, like, light doesn't produce from cool gas, so this doesn't make any sense at all. I don't like C. So the light produced from a hot solid that passed through a cool, this is going to produce what do you call that? Absorption spectrum. Why can't I am having problems here. Absorption. Yeah, there you go. That makes sense. Okay. So I had to look up the spelling. I don't know why I was having problems with that one. Absorption. Which would be like dark lines. Dark line. Spectrum. All right. So the answer is A. It's going to produce, like, hot solids or hot liquids are going to produce a nice continuous spectrum. The whole rainbow. Right? This is the full rainbow. That's what they mean by that. Cool. Okay, so we got a free electron. It has a certain amount of energy. It's coming along. So the key is this free electron comes along and collides with this hydrogen atom where there's an electron sitting here at energy level 2. As a result, where is this going to go? So remember, there's a difference between photons and electrons. If this was a photon, you might have got a different answer, because the photons had to have exactly the right amount of energy to get to the next level. Otherwise, it just passes straight on through. Electrons are allowed to give up a little bit of their energy. So in this case, I just want to know where would it go? Like, this is the energy. If it were to give it all up, where could it go? All right, so I'm going to add 2 electron volts to where it is right now. So it's kind of saying its change of energy could be 2 electron volts, which is like equal to final minus initial. I'm going to add over that initial amount. So I'm going to have like 2 electron volts plus this 3.40 electron number here. Okay. Well, minus. I should probably use the proper numbers that we had here. So let's actually write out everything that I'm doing. So 2 electron volts, final minus a negative 3 electron volts. Okay, so 2 minus 3.5. So what I get from my final could be negative 1.4 electron volts. But the problem is negative 1.4 lands right here. Right, that's where negative 1.4 is, somewhere between 3 and 4. All right. So where am I going to go? I'm going to go 3. All right, it's going to make it to 3. Now, if it wasn't a photon, the answer would be 2. Right? Not enough energy to get me exactly where I need to go, so I'm just not going to use it. It's just going to go back to where it was. I'm not even going to move. It's not even going to bother. Okay, Compton and de Broglie hypothesis, the wave particle. Remember, Compton was talking about, like, waves have momentum. De Broglie was saying things with momentum behave as waves, like particles act like waves. So like that way and then this way. So wave-particle duality. Cool, people. Oh, we're getting right to the end here. Where are we? It's only an hour and a half. Pretty fast here so far. This is actually a pretty short exam, isn't it? 40 plus 10, so that's 50 questions. Not too bad. That's about the size. Hour and a half. We're not done yet. Maybe this is going to take a while. Okay, which of the following equations could be related to the fusion of calcium and plutonium in the production of un-un-cudium? Un-um is a fluvium now. Like they actually named it. This back here, they didn't have a name back in 2009 when this test was made. Or 2008? 2009. Okay. Calcium, doubly charged, accelerates, fuses. They are repeatedly accelerated by an electron, but then one stage enters the chamber and exits at a certain speed. That might be for something else. Maybe for like a charge to mass ratio or something. Okay, we'll go with that. All right, so now we just have to figure out which of these actually works, I guess, because it didn't specify. It just fuses them together. It's going to produce an alpha particle. So the first one's not going to work because the bottom numbers, this would be charge, and the top is nucleons. They have to be conserved, right? So if the bottom numbers don't add up, then nothing works here. So if I go 20 plus 94, I get 114, but the other side I get 116. So this is just too much, right? So this one's not going to work, right? The next one, too little, like this is not going to work either. Conservation charge doesn't work here. Okay, the bottom one, the conservation charge works, but now I got to look at the top. 48 plus 244. 248 plus 244. I get 192, and then this one here is just too much, right? So that's got to be okay. So this is the only one that works because I need 292 on both sides. Sorry, not 192, 292 on both sides. So conservation charge and nucleons, that one works. Electric potential difference in the accelerating chamber. Okay, so to find out that, the electrical potential difference, I'm just going to figure out what the change of energy is divided by the charge. So they say this is doubly charged. So the charge of this is 3.2 times 10 to the negative 19, because it's 2 e's, right? Plus 2 e's, right? And my change of energy is going to be my final minus my initial of whatever form of energy I'm talking about. In this case, it's going to be kinetic energy. So I had to do the kinetic energy calculation twice. There is a shortcut, but I never remember correctly what it is. I might as well just calculate the two things. 1/2 mv squared final minus 1/2 mv squared initial. And then we get my answer. So times my mass. What's the mass of the calcium? We're talking about the calcium, right? So in this stage, we're talking about this. They want to know in this stage here, the calcium ion enters in here. Is the mass of the calcium ion up here? So these guys go together, right? Doubly charged. That's that one, right? So those are all in there. So just typing numbers into my calculator. And I gotta make sure to divide by 3.2 e to the negative 19. Oh, look at that. So what I get is 816,211 volts. So that's going to be C. Cool. All right. Magnetic strength to contain. So this one here is going to go in this little radius here. We're trying to find B. So what causes the radius is going to be a magnetic field. So I have to write my work up here. So. Okay. So here I got Fc is equal to Fm. Fc is equal to mass times acceleration. QVB. What acceleration we're going to use? Has an exit speed, and then immediately, so I got a speed here, and I got a radius that I have. I'm trying to find B. Okay, so mv squared over r qvb. We're trying to find b. Yeah, b. So mv squared over r qv. Cancel out one of those v's there. And you just punch all the numbers in. Okay, so I got the mass again. This is still the, yeah, still the calcium. Okay, we got the speed. No longer squared because I crossed that off. Divided by the radius. The radius is probably in centimeters. Oh no, it's in meters. That's nice. And I got the charge. Doubly charged again, so make sure you put the double charge in there. So 5, 5, yeah. What do we need here? So we need, so this is my answer. It's going to be 0.52, oh, 55, sorry, 55, my bad. 55166 Teslas. So if I'm going to fill in the boxes, I'm going to put scientific notation. Horrible for that. Like, I don't know why you do this in scientific notation, but that's what they want. Oh, that's a horrible box. I've been drawing really good boxes lately, but apparently not now. Okay, so we want A, B, C, D. There you go. Cool. All right, so in this decay chain, we got that turning into whatever 112 happens to be. What is 112? It's like palladium turns into copernicium, probably, Copernicus, and then it changes into DS, whatever DS happens to be. Darnstandium. All right. What are X and Y? All right, so this one here, I can see that it's lost 2 and lost 4. Minus 2, minus 4. So that's definitely an alpha particle. And then here it lost 2 again. And it lost 4 again. So definitely alpha particles. All right. Half-life is 30-some seconds. Okay, so half-life, my period for my half-life is 30.4 seconds. The time I'm going is 1 minute, which is 60 seconds. So it's approximately 2 half-lives. So if I divide this number by 2 really quickly, twice, I'm going to get something approximately 8, because it's approximately 2 half-lives. And the number of half-lives, remember, is equal to T divided by P, which is 60 divided by 30.4, which is 1.97 half-lives. Right? So I just quickly divide by 2 twice. Or we can just plug into our formula here. Right? So we got n that we're trying to find. We have n naught. We have a half raised to the power of my number of half-lives here. So 1 microgram times a half, 1.97 in my exponent there. Half to the power of my answer times 1. Hey, look at that. It's exactly what I was planning. Yeah. Yeah. So I could just divide by 2 quickly, because none of these answers are anywhere close. The product of the radioactive decay that penetrates matter the least is the alpha particle because of the size, more massive, right? So this is definitely going to have to be alpha because largest, right? Because of its relative, because of its relative mass is large, okay. So that just makes sense. Okay. The smaller it is, the more likely it's going to penetrate into it. Like, which of the following statements provides a reason for nuclear fusion rather than nuclear fission as a source? There's reason to use nuclear fusion rather than, okay. Fusion reactions produce No, probably not. Fusion energy is in the form of heat. Fission is in the form of gamma. No, that's not true. It's mostly heat. They all produce like gamma radiation. Fusion products are relatively harmless. That's probably true because they produce helium and stuff. Fusion is not economically feasible, whereas fission is not. Okay, fission is what we do now. It's the most economical feasible because it happens like pretty spontaneously, relatively low temperatures. You just shoot some neutron at something and it just kind of breaks apart. Fusion requires like lots of energy, really, to slam those things together, release that energy. So chances are the amount of energy released is not as much as you put in. I'm going to go with that answer because you're most likely producing like helium and stuff. You're producing beta particles that fly off, but those are going to be trapped pretty easily. No, that's not true. That's not true there. It produces in forms of heat because they use turbines and stuff. Fusion reaction to produce magnetic field. No, you have to produce fusion in a reactor as well. Yeah. When an electron and a positron collide, they annihilate, all their mass is converted. What's the energy released? So the energy released is going to be this mc squared formula, but the mass here is the mass of the two electrons, one positron, one electron, right? So this 9.11 times 10 to the negative 31 kilograms, plus another 9.11 times 10 to the negative 31 kilograms. Because an electron and a positron, when they collide, they're going to release all this energy, but the masses are the same. Because one's just an antiparticle, it just means the opposite charge, but the same mass. Okay. And this is just the speed of light squared. All right. This will end up being joules, so this is actually pretty nice. So I don't have to worry about converting the units here. So 1.6398 times 10 to the negative 13 joules. Quite a bit of energy there. All right, so two types of pions are modeled by consisting of a down quark and an anti-up quark, and an up quark and an anti-down quark. The only possible charges of these types of pions are, all right, so a down quark. No, I have to go by formula sheet here. A down quark is negative 1/3. So I'm just doing the first situation here. We've got a down quark and anti-up quark. So we have down quark. Yeah, I'm going to cross these ones off. Remember our thing was that they had to be whole number charges. The pions, if they're going to be a hadron at all, they got to have a whole number of charge. So we're going to cross those off. Not, well, actually integer charges. Okay, so this is my down and an anti-up. Anti-up is a negative 2/3. If I add them together, I get negative 3/3, which is negative 1. Ah, that doesn't help. Okay, my next one is going to be an up and an anti-down. So 2/3, 1/3, 3/3, positive 1. So it's got to be C. There you go. And we're done. All right, cool. All right. I will see you probably in the next video. Bye.